For the past few lectures, we've been focused on recursion, and today we're going to continue to get more practice and exposure and experience working with this subject. A few announcements before we get into it. First, there's a review session that will be led by the undergraduate teaching assistants tonight from 4 to 5 p.m. Eastern Time. The link to this Zoom-based review session will be on CourseCare about 10 minutes before we get started. The last review session had a really great turnout. There's great interactivity from chat. We expect to see the same at this review session. I highly encourage you to get a different perspective on this recursive subject from your UTAs tonight. Next, if you are considering continuing on in computer science, that's great. I'm excited to hear it. The new introductory sequence in computer science, which is rolling out this fall, will apply to you. And that's good news because I believe this is a big improvement from the previous introductory sequence we had. And I've spent the last few years helping to shape this. But in today's slides, you'll find 2 links that I think you'll find very helpful in understanding what the sequence of courses that you can expect to take looking forward is for the minor, the major, BA, or BS. And I recorded a YouTube video trying to explain the sequence of courses as they will be in the future to give you a better sense of what to expect looking forward, because we have all new numbers in a much better outcome for the introductory sequence. Lastly, there have been some questions about how do the grade scope questions work. Well, 2% of your grade in class before we broke for spring break was decided by your participation and your responses to the challenge questions in lecture. And 3% was based on some of the warm-up questions that we did beforehand. For these grade scope lecture questions, we're going to try and spread it out just the same way. If you turn something in, no matter what the outcome is of that score, you'll get credit towards your 2% completion. And on the correctness side, we're looking for really about 75% correctness on your responses to these grade scope questions will get you 100% credit, right? So we're not looking for exact 100% on everything because we're mixing in some challenge questions, and I wouldn't stress too much about this, but because there are some questions here, I just wanted to put out that little bit of extra information on what to expect moving forward. So let's jump into a challenge question. In this challenge question, you can respond to it on poll, or not on poll everywhere, on Gradescope. And the question has to do with types. Now that we're working with these lists and these generic node types, you've seen these 3 functions before. The question is, what are the types of the variables x's, first x's, and rest x's? So go ahead, pause the video at this moment, think through, given the context of what these variables are being initialized to hold as their values, and based on that, try and figure out what would their types be if you were to explicitly declare them as part of the declaration statements. All right, hopefully you got those. If not, this is a great type of conceptual question to come ask us in office hours, which are once again open this week. I'll give you the first one here, and then I'll leave the second 2 to you. So in this first line here, we see that we are assigning to this variable named x's the result of calling the cons function. We're constructing a list here, right? So we're constructing a list, and the innermost cons is saying, okay, we've got the number 2 followed by null, meaning that's the empty list or the end of our list. Because we're working with a linked list here, and we're consing 1 onto the front of that, right? So 1 is followed by 2 is followed by null. And so the types of each of these nodes is node, and then the generic, the concrete type for what was generic for this type T is going to be specifically number here, right? Because once we actually have values for any of these nodes, their type will need to be concrete when our program actually goes to run. And here, because we used numbers to build up this list, the type of x's would, of course, be node number. That's its concrete type, rather than node t, which was in this cons definition, that was the type of the list parameter as well as the return type of that particular function call. In this next environment diagram, what you're going to see is we're going to use this exact same notation and visualization for nodes in our linked list if we need to think about how we represent them in an environment diagram. So keep this in mind as we move to the next question. Right? Before we get into that, there's one other utility function that's built into our library I want to show off because the next environment diagram question uses this, and I think you'll actually find this particular function very helpful when you're working on the current problem set. Right? So the idea is we've got this listify function. So let's take a look at this in code. And so you'll notice I've imported the listify function as one of the functions from the intro.cs list library, in addition to first, rest, and cons. And what we're going to do here is make use of that function by setting up a variable. Let's call it names. And that will be assigned the result of calling this listify function. And now we can give as arguments the values that we want to be in our generated list in the order we expect them to be in that list. So for example, I could do things like Kelly Hogan, Mara Evans, and let's say Giddy Schemmer, a few biology instructors, right, at UNC. And so we've got these three names in this list. And now if I print that list of names, what you'll notice is we've got a list of nodes that are printed out here. And if I were to have said, okay, the names or bio instructors are, and concatenate that list of names, we would see it in textual format, Kelly Hogan, Mara Evans, Giddy Schemmer. And if we were to use the functions first and rest, we can access those values, right? So first of the rest of the names is Mara Evans, right? And so what listify will do is build a list of nodes in the order of the arguments we provide. So for example, if we look at the type of this names variable, we see that it's of type node string, right? And so this is really a handy way because we would have needed to cons Kelly Hogan onto the cons of Mara Evans, onto the cons of Giddy Schemmer, onto the cons, or onto the null, the empty list, right? And underneath the hood, the implementation of this function is doing that exact same thing, but this winds up being pretty handy for quickly constructing a list of nodes in a specific order. In listify, we could have used numbers here if you wanted to test with numbers, and I would encourage you to make use of this in the current problem set for generating test lists to work with your functions. Right? So now that we've gotten that out of the way, let's take a look at an environment diagram question. So let's trace through this environment diagram. And what we're going to be focused on is understanding how to make use of these functions which we imported without actually adding frames to the stack for them. Right? So we are going to need a heap in this diagram. And in diagrams that involve linked lists, we know that each of those nodes is an object that's living on our heap. And then I'm going to also set up my stack, right, for the frames of execution that my program will go through. We're going to have a globals frame, and in the next unit, the next set of lectures, we will pay a little bit more attention to globals and add to the things that we know exist in globals. But for now, we don't need to worry about it. And what we do know, because there are no global variables defined elsewhere in this program that are values, and we do know that our main function is going to start on line 18. So the return address of this call to main is line 18. There are no parameters for us to set up, so we're ready to jump right in. And the question is, what happens when we call this listify function, which we imported from a library, right? Now, we could go look at the source code for that, and that's what the computer would need to do, right? The computer would need to go jump into the listify function, add a frame for it, walk through its lines of code step by step by step. But for our purposes, what we're going to do is we're going to treat these four functions as special functions whose return values we can just depend upon, right? We're going to treat these effectively as identity functions that we know as the people thinking through this particular diagram, and we can trust that those functions are properly implemented so that we know what to expect. And we've already been doing that this semester with the print function, right? Whenever we call the print function, in our environment diagrams, we just add to an output column. We don't jump into the print function. We don't add a frame for it, but the computer would do all of those things and would need to jump into a print function with a frame for it if it were actually evaluating it. But the same idea here, where we know what listify does, right? So what listify does is it returns to us a reference to a list, right? So I'm going to set up my x's variable here. And we know that each node of the list has a type of node and then a concrete type. And in this case, the concrete type will be number because we're setting up a list of numbers. So I've got a node of type number. Now, in the past, when we've added objects to our heap and we've had the class definitions of those objects types written out in the code of our environment diagram, we've written out each property value that that particular object has in the heap. But we're thinking about these nodes in this linked list as in an abstract form of a list of numbers. So all we're going to do to represent this particular node is add the number that is stored in its value. And then it's going to be followed by some other node, right? In this case, that node's value is going to be 2. And that's going to be followed by another node whose value is 3. And we know that all lists must be terminated or end in a null value, right? And so null would be the last value of this list if we wanted to represent it in this way. Other perfectly fine ways of representing this, I could have just drawn 0 with a slash through it, and that's fine too. Right? We don't need to write node of type number for each of these other node entries because it's implicitly got to be that, right? If the first node is node of type number, the next node and all nodes that follow must also be of that same concrete type. Right? So when we see listify in a given environment diagram question, we can assume that those nodes will be set up for us, and you're going to have on the heap some objects that look like this. Now, of course, these objects have properties like a next property and a value property, but we're abstracting those details away when we're thinking about this in terms of just these 4 functions, right? So x's is just a list, 1, 2, 3. And we're ready to continue on. So when we call the sum function here, we know that we need to add a frame to our stack for it. And the return address is going to be line 6. And we are passing in x's, whatever x's is. So it's a reference to this first node, right? And I can make that even more explicit here, to the list parameter. So we're going to have a parameter named list. And it's going to refer to this very first node in our linked list, right? We get to this if statement and we ask if list is null. That's not true, so we're going to go to the else branch. And in the else branch, we're setting up a variable x to be the first value of the list. So before I turn it over to you, let's just think through this. Now, normally, because this is happening in a block, we would add, a block to the diagram, but for space purposes, and because there's nothing that follows after this block, right? This is the only code that's going to be evaluated here. There's no opportunity for X to be used anywhere outside of this accidentally. So I'm not going to add a block to my diagram here. I'm just going to add a variable X whose value is the first of the list. Now this is a function call, right? We would have to jump to some first function. The computer would have to add a frame to our stack for it, and it would return a value. But what we know about first, just by virtue of this being a predefined function for us, is that it's going to give us the first value that's stored in this list. In this case, it's going to be the number 1, right? So the first value of this list is 1. And then what we're going to do is we're going to return x added on to some of the rest of the list, right? So here's our recursive step, right? So we need to add another frame for sum. And this return address is going to be line 14, right? And this time around, we're passing to the list parameter the rest of the list that was in the previous frame, right? So if this list in the frame that we're calling this function from was referring to the first node in this list, then the list in this second frame is referring to the next node that follows it, right? And everything that comes after it. And we're ready to jump into this sum function frame, right? And at this point, we are back at line 10 and our current frame is this one. And I want you to pause the video here and see if you can complete the rest of this environment diagram based on what we've seen so far. All right, great. So let's keep working through this together. And at this point, we are assuming, or we are evaluating, is list equal to null? List is not equal to null. List is currently referring to the node whose value is 2. So we go to line 13 again. And here we're saying x is the first value of this list. So x is going to be 2. And we once again reach this return statement. But before we know what to return here, we need to call the sum function again. So sum. And the return address, the return address is going to be line 14. And the list that we're referring to is going to be the rest of the list of the previous frame, right? So in the previous frame, the list referred to the node 2. So in this call to sum, list refers to the node whose value is 3. And we are ready to jump into this function call frame, right? And so in this frame, we ask, is list null? Well, which list are we talking about? We now have 3 list values on our stack. But remember, the frame that we're currently working in is the lowest frame on the stack that has yet to actually return a value, and that would be this current frame. So list is referring to the node whose value is 3. That would not be null, so we don't go into the then branch yet. We once again hit this x is assigned the first value of the list, so x is going to be the value 3. And then we once again hit this return statement. So return, and we need to set up another frame on our call stack for the sum function. The list that's going to be referred to is the null value here that we that came after 3, right? So the rest of the list was just null, or the empty list is all that was left at this point. And the return address is once again line 14, right? So we jump into this frame because this is the lowest frame that we haven't completed, and we're starting a brand new function called a sum recursively. And now we reach our base case, right? So this is our base case because inside of this then block, there's no recursive call to sum, right? So when list is equal to null, in this case, that's true because list now refers to null. What we're going to do is we're going to return 0, right? So our return value is going to be 0. And where are we sending 0 to? Well, we're sending 0 to line 14, right? To this call to sum, right? But now the frame that we've returned back to, right? Because we need to work our way back up the frames of our call stack. The frame that we return to is this one. And so 0 was the value of summing the rest of the list when the rest of the list was null. And now we have to evaluate, well, what is x plus 0? Well, what is x? And in this frame, which is the current frame we're working in, because remember, it's the lowest on our stack that hasn't yet returned a value, x's value is 3. So what we're going to return here is 3 plus 0, or 3. Right? So the return value is 3. And where are we returning 3 to? We're returning 3 back to line 14. Right, where the sum call occurred. So this was the recursive call. And so now we have 3 plus x. And so we're asking ourselves, well, what is x here? Well, currently, the frame that we're working in is this one, right? Because both of these frames have returned their values and are done with their jobs. And now we're trying to figure out, well, what is the return value of this call to sum that happened recursively? Well, x's value is 2. So we're going to add 2 plus 3, which would be 5, and the return value will be 5 in this frame, right? Well, where are we returning this value of 5 to? We're returning it right back to that recursive call on line 14, right? So that call happened on line 14 that was recursive. We return 5 back to it. And so now we are in this frame for sum. This call to sum that was recursive evaluated to 5, and we need to figure out, well, what is x plus 5? Well, once again, we're in this frame on the stack because it's the lowest that hasn't returned. And x's value is 1. So we're going to have 1 plus 5, or 6, as the return value here. So the return value is 6. And it's a coincidence that we're returning the value of 6 back to line 6, right? But that's where the call occurred at. So 6 is returned to where this initial call to sum happened. And now we can print out the output here would be 6. Right? And then we're done with that print statement, and we return nothing from main, and our program's done. There are a few things, I shouldn't have deleted the output, so the output was 6, right? There are just a few things I want to point out about the pattern that we're seeing here. notice that as we made our recursive calls, and let me actually use a different color here. As we made our recursive calls, we were moving through our list, right? So we started here in our list, and then we moved on to the rest of the list, which would give us the sublist 2, 3, and then we moved on to the rest of our list, which was the sublist 3 followed by null, and then the sublist at the end was just the empty list, right? And once we got to the bottom, we once again worked our way back up, right? And this is the common pattern with a recursive function. You have to work your way until you hit the base case, and then you're unwinding yourself back up. And if that recursive call happened as a part of the return value, which we're seeing here, that recursive value that was returned is going to be substituted in where the call occurred at. And we saw that pattern here, and you'll get a chance to practice that in the next video or in the next challenge question as well. In this challenge question, we're once again seeing a recursive function. We are once again seeing a recursive function call as a part of the return statement. But I want to try and turn it over to you before we even get started to see if you can apply those same principles we just learned in the last environment diagram question and reproduce it here. So pause the video, try producing this environment diagram. This is really great practice with recursion and these functions that we're seeing that are revolving around lists and nodes. So go ahead and work on this, and we'll come back in just a few more minutes. Okay, so I'm going to set up my heap, and I'm going to set up my stack. Once again, the stack is going to have a globals frame. There are no global variables that we care about yet, so I'm going to leave that empty. And the heap begins empty, but we'll see that we very quickly add values to it. And we start our program with a main function. And our main function call happened on line 18. So that's where the control would return back to once we've evaluated it. There are no parameters. So we set up our main frame and we're ready to jump in. Once again, we see we're setting up a variable named Cs that begins a list of type node string. Right? So this is a list of string values, and the first string is the string, just the letter A, right? And this is going to be followed by a node with the string B as its value, followed by a node with the value C, and that would be followed by null or the empty list, right? So we reach a call to print G of C's. And G, of course, is the recursive function we're going to evaluate. It works pretty similarly to the one we just practiced with, but has a slight difference that hopefully you caught on to as you worked through it yourself. So I'm going to set up a frame for G. The return address here is from within the main function at line 6. And the N parameter is going to refer to C's, right? What C's was in main, N is going to refer to in this call to G, right? So we very quickly see that this is following a very similar pattern to before. The base case happens at first, and N is not equal to null, so we're not going to evaluate that. And we're going to set up a variable named S, whose value is the string A, because that's the first value of our list of nodes, N. Right? Once again, these variables are inside of a block, right? But because there's nothing that came after this block, and I'm tight for space here, I'm going to leave out the notation of that block and the lines that it spanned here. But technically, S would only be defined in the block from lines 12 to 15. Right, so we now reach a recursive function call. And before we know what to return from this call to G, we need to go evaluate the next call to G. So G is going to have a return address of line 14 here. And the parameter N is whatever rest of N is in the node, in the frame we're coming from. So N in the frame we're coming from was starting with A. So the rest of that list is the node B and what follows it, right? So we set up our frame, we're ready to jump in. N is not null, so we go into this else. S is once again the first value, so S is going to be B, and we hit this recursive call again. And I'm going to move pretty quickly through this sequence of recursive calls to try and get to the interesting part more quickly. So here N is going to be the next node, or the rest of N that came before it, so that's going to be referring to this node whose value is C. When we jump into this, n is not null, so now s is going to be the value c. And we reach the return statement one more time, and we're calling g for the last time here because we're going to be passing in the rest of the list, which is the empty list, right? So the return address is line 14, and n is going to refer to null, the empty list. This time around, right, we now hit the base case because n is null. And so here we're saying the return value of this frame is, and I'm going to write it over to the side here, the return value is exclamation point. Right? So it's the exclamation point. Where are we returning the exclamation point to? We're returning it to line 14, right? So on line 14, but in the frame where s's value was c and n was the list you began with the c node, we've returned this exclamation point. And now we need to be very careful here because notice this return statement is saying return the result of that function we just finished evaluating, who returned a exclamation point to us, concatenated with s. Well, which s are we talking about? Again, the current frame that we're working in, whose variables we need to be looking at for name resolution, is the lowest frame on the stack that hasn't returned. And in this case, that value of s is c. So we see that we are going to return exclamation point concatenated with c in a string, right? And notice that this is a little bit different and a little bit tricky versus what we did before. The recursive call came before the value that we're concatenating on. So we have exclamation point c as the return value of this frame. Right? And we're returning that where? We're returning that to line 14. Right? So back now in the frame where s's value is b, we've just returned exclamation point c as this recursive call. So now this return statement is going to read return exclamation point c concatenated with whatever s's value is in the current frame we're working in. When this frame, that value is the string b, right? So the string b is going to be concatenated onto exclamation point c. So the return value is going to evaluate to exclamation point CB. So let me write that in here. So the return value of this frame is exclamation point CB. And where is that string being returned? Well, we look at the return address of this frame and it says return that to line 14. So line 14, that call to G happened here. But now we've moved back up our stack to this frame, right? So this is now the frame we're working in. So we're going to return from this frame that string plus or concatenated with s, right? Well, what s are we talking about? We're talking about the s in our current frame. So that would be the string a. And that would mean that we're returning a value of exclamation point CBA from this particular frame. So the return value is exclamation point CBA, that's a string. And where are we returning that to? Well, notice this was our initial frame for G. This is where the recursive process began. So our return address is no longer inside of the function G, but it's back to where we initially called it on line 6, right? So on line 6, that's where we need to return this value back to. So now we're in the main frame, and when we return back with this CBA string, the output that's printed to the screen would be exclamation point CBA, and that would be a string value. And then we reach the end of main and our program is done. Right? So the only real difference between this example and the previous one is just paying attention to the fact that these are different types of our list and being very careful with thinking through how a return statement is going to be evaluated when recursion is a part of it. So notice we were able to reverse our input list and concatenate those nodes backwards if we had done s concatenated with g of rest of n instead. Notice if this was our return statement and we flipped that concatenation, so return this, we would have ended up with ABC exclamation point, right? And if you want to think through why that is, that's another good exercise as well. But these are the environment diagram questions to give us a sense of how to work through questions which involve nodes as a part of them. And next we're going to practice some code-based, get some more practice with some code-based questions. So great work on these. This recursive process is tedious to work through at times because we're adding all of these frames to the same function, but hopefully seeing each of these frames stack up and then working our way back through them as we saw here. So working our way back up each of these frames on the stack really helps give you a feel for how it is that the computer is able to achieve recursion underneath the hood.